Hello, my name is Katarina Vučković. I am a PhD student at the University of Central Florida and a member of the Communications and Wireless Networks Lab. Today I will be presenting MAPCSI, single-site map-assisted localization using massive MIMO CSI. Here is an overview of the topic that I will be discussing. First, I will present the motivation for this work. Next, I will summarize the different localization techniques used in the past. This will be followed by a system model and a channel model description, which will lead into the MAPCSI, which is the map-assisted localization technique. I will also discuss the dataset used for this work, and after that I will present my results and discuss them. I will conclude by summarizing the work and highlighting the main points. In recent years, many applications emerged that require highly accurate positioning systems. Some of these applications include air traffic management and navigation for unmanned aerial vehicles, navigation of self-driving cars, indoor localization of assets and people, such as localization of patients in hospitals, or baggage localization at airports. Finally, many of our mobile applications require localization. Currently, most of these applications rely on GPS. However, GPS is only accurate within 5 meters. Furthermore, its performance degrades in urban canyons and is inefficient in indoor environments. Therefore, there is an evident need for alternative positioning systems. There are several different categories of localization techniques. Triliteration and triangulation are two techniques that rely on intersection of incoming signals from multiple anchor nodes. The disadvantage of this technique is that they cannot be used for single-site localization. Fingerprinting is a technique that maps wireless channel measurements to each location and environment and then trains a neural network to make predictions based on the new measurements. The disadvantage is that the measurement campaign and training of the neural networks are two complex and laborious tasks. Finally, we introduce map-assisted localization techniques. In this approach, the propagation paths are superimposed on the environment map to localize the user. MAP-AT is a previously proposed localization technique that assumes that the angle and delay of each path is known. Communication systems typically don't measure these parameters, so obtaining them introduces additional complexity to the system. Therefore, we propose MAPCSI. CSI data is used in most practical systems to estimate the link quality. Thus, using this parameter does not create additional burden to the system. In subsequent slides, I will discuss how angle and delay can be extrapolated from CSI. For the system model, we assume a single user operating with an omnidirectional antenna and a base station equipped with a MIMO antenna. The MIMO antenna is a uniform linear array antenna with NT antenna array elements. Furthermore, the system uses the OFDM signal modulation scheme with NC subcarriers. Each path between the user and the base station can be characterized by a delay, an angle of departure from the base station, and a complex gain, where C is the number of distinguishable clusters and RC is the number of paths within a cluster. In this slide, we define the channel state information, or CSI. The channel frequency response, or CFR, for each subcarrier L can be written as shown, where E is the rate response of each ULA antenna. Then, the CSI matrix between the user and the antenna can be expressed as a combination of all HLs for all NC subcarriers. The CSI contains all the necessary information. However, CSI in its raw format is not visually interpretable. To achieve a meaningful representation of CSI, it is necessary to convert it to angle delay profile. ADP is a linear transformation of CSI computed by multiplying two discrete Fourier transform matrices. Let us define the DFT matrix V of size NTT by NP and matrix F of size NC by NCC, where NTT and NCC are arbitrary integers larger than NT and NC, where NT is the number of antennas and NC is the number of subcarriers. Then the ADP matrix is defined as shown, where the size of the G matrix is NTT by NCC. In prior works, the ADP was defined using square DFT matrices, which means that the size of V was NT by NT and size of F was NC by NC, thus limiting the size of the ADP to NT by NC. We introduced the NTT and NCC integers to increase the size of the ADP. By increasing the size of the ADP, we were able to improve the accuracy of the localization network. This slide explains the correlation of the ADP and the environment map. The graph on the left-hand side is an ADP at some time instance t. The intensity of the ADP shows where the dominant paths are located. This ADP has 5 dominant paths, each labeled with a different color box. The horizontal axis shows the delay and the vertical axis the angle of departure of each path. So the path in the orange box has a delay of about 135 nanoseconds and an angle of 22 degrees. Relating this to the environment map, we observe an orange line that represents this path. The length of this line is equivalent to the distance traveled in 135 nanoseconds, and the angle of departure is measured in the horizontal axis in the counterclockwise direction. A similar analogy can be made for the remaining 4 paths. The figure on the left shows a map-assisted localization technique. First, the dominant paths are projected on the map using a recurrent reflection model. As shown in the figure, each path has multiple squares indicating candidate user locations. Multiple candidates for a single path stem from the ambiguity associated with recovering the delay from the ADP. We use silhouette coefficients and k-means to cluster the candidate locations. The centroid of the densest cluster becomes the estimated user location. On the right-hand side, we explain the ambiguity of the delay. The actual delay equals to NMK times TS, while the maximum delay that can be captured by the ADP is limited to NC times TS, where NMK is the sample delay belonging to path M of cluster K, TS is the sample interval, and NC is the number of subcarriers. If NMK is less than NC, there is no ambiguity. However, if NMK is greater than NC, then the ADP wraps around and the remainder shows up in the ADP. For example, if NMK is 70 and NC is 60, then the ADP will show 10. Since we don't know how many times it wraps around, we have to consider at least 3 candidates at 10, 70, and 130. The number of candidates for a given ray will depend on the environment. For this work, we utilize the YY dataset. The YY dataset is a public MIMO dataset intended for machine learning-driven research in wireless communications. On the left-hand side, we have 2 scenarios. On the top is the LOS dataset. This dataset has all samples in line-of-sight view. It has 5 locations in the y-axis and 1,000 locations in the x-axis, resulting in a total of 5,000 locations. The bottom figure shows the mixed dataset. The mixed dataset is the same as the line-of-sight dataset, except that it has 2 buses obstructing the view of the line of sight for some locations. Approximately 1/2 of the samples has the line of sight view obstructed. The table on the right shows the other parameters associated with the dataset. We utilize a frequency band of 60 GHz with a bandwidth of 500 MHz and a base station antenna aligned in the x-axis. Furthermore, we use the number of antenna elements of 60 and the number of subcarriers 60, and the number of paths was set to 25. The results for the LOS dataset are shown on the left graph, while the graph on the right shows the results for the mixed dataset containing both LOS and NLOS samples. The average error in meters is computed for different NTT and NCC coefficients. The horizontal axis shows the different NTT values ranging from 30 to 180, and each curve in the graph is a different NCC value ranging from 60 to 180. The average error in meters is shown on the vertical axis. There is also a dotted line displayed on the graph. This line represents the error of MAPCSI method. In MAPCSI, there is no error associated with estimating angle and delay, unlike in MAPCSI. Therefore, MAPCSI can never exceed the performance of MAPCSI. However, if it is designed well, MAPCSI can approach the accuracy of MAPCSI. Therefore, MAPCSI is considered a lower boundary limit. From the graph, we conclude that the accuracy of MAPCSI improves as NTT and NCC integers increase. The best accuracy is achieved when NTT and NCC are 180 with error of 1.8 meters for LOS and 2.8 meters for mixed dataset. In this slide, we further examine the mixed dataset by splitting the results into LOS and NLOS samples. We observe that increasing the coefficients improves the accuracy of both samples. Furthermore, comparing the error of the LOS samples in the mixed datasets to the LOS samples in the LOS dataset, the error is similar. This means that the bus obstruction did not impact the results for the LOS data. However, the results for the NLOS data increased. The error comes from blocking one or more critical paths. When this occurs, the number of candidate user locations in the cluster is reduced, and as a consequence, the classifier selects a cluster that is farther away from the actual user location, thus resulting in an increased error. To conclude, we introduced a map-assisted localization approach for single-site massive MIMO systems using CSI and the environment map. We redefined the formulation of ADP to increase the angular and temporal resolution by introducing NTT and NCC coefficients. We proposed a clustering and classification algorithm based on silhouette coefficients and k-means to estimate the user location from the candidate user locations. Finally, we benchmarked the performance of map-assisted techniques on a public dataset and showed that if ADP is large enough, the accuracy of MAPCSI can start to approach MAPCSI. Thank you for listening to my presentation. The code for this work can be found using the link shown. Also, if you have any questions or would like to discuss this topic further, please feel free to contact me via the email provided here. Have a nice day and enjoy the conference.